Buffers yet again, and now in this case we'll be finding out a little bit about pH changes if you add a little bit acid or base to a buffer. So what is the new pH of a solution made from 0.405 molar formic acid and 0.326 molar of the sodium formate if 1.00 milliliter of 0.25 molar HCl is added to 50 milliliter of the buffer, and all the volumes are given to you because you need to calculate concentrations eventually, okay? And otherwise the volume would not be that important. Then you can work with 1 liter, but here it seems that the volumes are important, so they're given to us. Ka is also given to us for the formic acid, and I need you to see the pencast for acid base 9, okay, for calculation of pH for this system, okay, because I've done this one before, just the first part, okay, on the pH, because we need the initial pH and then we're going to talk about what the change in the pH was, okay. So if you need to look at how to calculate the pH of this kind of a system, you can look back into that. Alright, so here is our equation, HCOO minus plus H3O plus to give us the acid and water. Why did I write it this way? It's because I'm adding acid to the buffer. So if I'm adding acid to the buffer, acid has to be on the left hand side. If acid is on the left hand side, then on the left hand side I also need the conjugate base, right, which is 0.326 molar. All right, so initial concentrations then of this one, and since the volume is given to us, I'm going to go ahead and calculate the moles over here. And so that is 0.326 times 0.05 liter. Okay, that is how much of the buffer we have, and the acid that we have is 1 milliliter of 0.25, okay, molar. So which means that the acid that's being added is 0.25 times 0.001 liter. That's the moles, okay, that we have. Moles of the acid are 0.405 times 0.05 liters because the buffer was 50 milliliters. Okay, so then the change, okay, that you're going to have is going to be for the smaller amount, okay, that you calculate. So let me write the calculated amounts that we have here. 1.63 times 10 to the negative 2, 2.5 times 10 to the negative 4, and then 2.025 times 10 to the negative 4. One second. (10 to the negative 2). Okay, so I had my calculation wrong there, but anyhow, that's what it is. So then at the change point, what we're going to have is remove the smaller amount of moles. So on the left hand side, since we're adding acid, the base is going to get finished up, which means this is going to be minus 2.5 times 10 to the negative 4. Of course, this is negative 2.5 times 10 to the negative 4. But the product side is going to increase by 2.5 times 10 to the negative 4 because once the reaction is happening, you're actually forming acid, okay, over here. So then at equilibrium, you have 0.01605 moles of the conjugate base. The hydronium ion turns out to be 0, so we don't have to worry about that anymore. And then our acid concentration is going to be 0.0203. Okay, so those are your new concentrations, but that is moles. And since you are calculating in Henderson-Hasselbalch equation or the other one, you can use moles also because the volume is going to be the same. So if you have the volume same, you can just take the mole ratios. All right, so the new pH then, H3O plus, is equal to, remember, Ka, times acid over base, and those are your concentrations then. So 1.63 8 times 10 to the negative 4 times 0.0203, that's our acid, and the base is 0.01605. And so then this is 2.32 times 10 to the negative 4. And then the pH is negative log of 2.23 times 10 to the negative 4, which is 3.63. So that's the new pH. Original one that you would look in the Pencast if you want to, original pH was 4.74. So the pH did not change that much, okay, if you think about it. So that's the property of buffers anyway, okay, is that the pH doesn't change if you add a little acid or base.